Howdy and welcome back to this series of lectures on linear algebra. Today we'll be talking, as the title says, about dot product and projections. Probably you've already seen the concept of dot product before, and most likely you have seen the concept of projection. Today, hopefully, I'm going to not only review these concepts in the context of the linear algebra jargon and framework, but also show you a few new things as well as the connections between these two concepts. The pictures that you see in front of you synthesizes both the idea of projection, and probably you have figured that one out, but it also includes the concept of dot product. And I'm not sure if you've already seen how that connection is made, but we're going to see that very shortly. So, what are we going to look at? This is the idea. For any geometric vector, we know that we can define the length of that vector through a formula that boils down to this. In two dimensions, the square of the length of a vector is the sum of the squares of its two components, and in 3D it's the sum of the squares of its three components. However, the square of a number is equal to the number times itself, so I can rewrite those formula in this way. That means that the square of the length of a vector is going to be equal to the sum of products, each product being the product of a component with itself. Well, this idea is what we're going to be generalizing. Remember that generalizing is a very central idea, very central activity in linear algebra, especially when it leads to useful and fruitful things. And this is one of those situations. So how are we going to generalize it? Well, we're going to define something called, not surprisingly, the dot product of two vectors, u and v, where u and v are going to have to be vectors of the same dimension, and we're going to define it as follows. I'm going to say that the dot product of u and v is going to be the sum of the products of the corresponding components. So u1 times v1 plus u2 times v2 in two dimensions. Of course, in three dimensions it's going to be exactly the same thing, but with three products. Okay, so it's nice and simple. It can be easily done. I'm sure that you will have no problems in calculating the dot product of two vectors, be they 2D or 3D. But the point is, what is this stuff for? Besides being a nice exercise in number crunching, what can we use it for? So what are dot products for? Well, we're going to find out that they are useful for a whole bunch of things, not only for geometric vectors but also for more general vectors that we're going to see later. So what can we do? First of all, it turns out, and this is something for which I'm going to refer you to the textbook, which has a fairly complete description of the proof of this fact, and it's fairly simple. It's probably easier to follow rather than me doing it here. But it turns out that if I have two vectors u and v, and I look at the angle that is formed between the two of them, then the cosine of that angle is actually equal to the dot product of those two vectors divided by the product of their lengths. Okay? So this is a very simple exercise in trigonometry, and again, it's an interesting one, but that I definitely recommend that you have a look at in the textbook. So this tells you right away that the dot product is definitely linked with the angle that two vectors form. In particular, we notice that the cosine of the angle between the two vectors is going to be 0 if and only if the dot product of those two vectors is equal to 0. Now, when does the cosine equal 0? When is cosine of theta equal to 0? As you remember from calculus and from your high school, the cosine is equal to 0 when the angle is either pi over 2 or 3 pi over 2. Which means that the two vectors in that particular situation form a right angle. Pi over 2 and 3 pi over 2 are 90-degree angles or 270-degree angles, but 90-degree angles one way or the other. And therefore, we can say that two geometric vectors are perpendicular if and only if their dot product is equal to 0. Now, this may look like a very small thing, but it turns out to be a very important one, and one that is going to be used later on in many situations, both algebraically and not, and in fact is going to allow us to define the notion of perpendicularity or orthogonality, as we're going to call it later, even for vectors that do not have a geometric meaning.